Good morning, good afternoon, and good evening, everyone. Welcome to today's Ask the Expert webinar on battery materials analysis. Our presenters and experts for today are Dr. Daniel Liu, Battery Testing Manager, Dr. Dranjan Sari, our Battery Scientist, Kelly Prohaska, our Battery Testing Analyst, and our moderator for today, Dr. Daniel Sullivan, our Senior Regional Sales Manager. My name is Rena Samsu, and I am the Senior Marketing Manager assisting with today's event. Before we get started, let's go over a few housekeeping items. All attendees have been muted. However, if you have additional questions that pop up during the presentation, please submit them in the questions section located in the bottom of your control panel. You may send in your questions at any time during the presentation. Time permitting, we will answer these questions during today's event, or we will follow up with you in the coming week. With the abundance of pre-submitted questions for today's event, we unfortunately will not be able to get to all of them during the presentation. For any unanswered questions, the team will send answers out to those questions soon. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. Now I will turn it over to our first presenter for today, Dr. Dan Sullivan.
Thank you, Rena. Welcome, everybody. Our experts will be here to address your questions on battery materials. We have some materials we're going to show and go through examples of things that can be done in the laboratory. We'll then going to be trying to answer the questions that we've seen ahead of time. And then at the end, our experts will go through and do a question and answer. But I did want to let you know about EAG Laboratories. EAG is owned by Eurofins. And our new battery lab has been functional this last year, and we'll be looking forward to meeting all of you and doing work with you and answering your questions. As you can see on the map here, over in California, we have 6 laboratories in the Bay Area, and the new star there is our battery lab. It's very close to our main FA lab, and if you'd like to come by and take a visit to it, please feel free to ask us and we can arrange that in the future. EAG does have 26 laboratories across the world. The other battery lab is the other star up in the northeast there, where we do ICP, ICP-MS on electrolytes and different battery materials. Next slide, please. This is our smart chart. We have posters of these. If you'd like one, let us know and send us a question and we can get you a poster. But we also have this on our website. This basically is called the spectroscopy microscopy analytical resolution tool. We also call it the Show Me All the Right tools. And this basically is a nice, handy reference to go to look at the different techniques and look at their detection limits, the area of analysis. And it's on our website in a way that you can actually hover over with your mouse and it will actually pop up and have a paragraph or two of explanation how the technique works. Next slide, please. Not only the area and the detection limits is important, but also the depth of analysis is important, especially when you're working on materials that have thin films involved. We have a variety of techniques that look at the very surface of materials like AFM and optical photometry that look at the very top surface, the top 3 nanometers. And then we have other techniques that look deeper and deeper, and then also bulk type analysis, such as GDMS and Raman. Next slide, please. So I'm going to hand this over to our expert, Daniel Liu, who's the manager of the laboratory, and he's going to go over and answer some questions.
Hi, good morning, everyone. My name is Daniel Liu. I joined EAG about half a year ago, and here are our new battery lab. I'm managing the battery testing service, so I would like to give you a broad introduction to our battery service. So at the EAG, we offer a comprehensive battery testing service, and as you can see, we can test the battery as a whole, and starting from the smallest coin cells to prismatic cells, cylindrical cells, to even the full EV packs. And we have a 3D blue LED scanner. We can scan the dimension and outside structure of the batteries or devices. And we have a capability to do the electrochemical testing as well. And also we have 2D X-ray or also 3D X-ray CT scan capability to do the all of this to do the non-destructive testing service for the batteries. And if the non-destructive method cannot find a problem, then we are also able to extract the component of the battery by just disassemble or tear down the battery to extract the electrolyte, any gas, or cathode, anode, or separator, extract them from the battery and do the subsequent analysis, like the morphology using our microscope or the chemical composition using our GCMS, NMR, FTIR, such etc. And furthermore, we can also extract the active materials or raw materials from the cathode or anode to get the raw materials and then to do the analysis on these raw materials, like the particle size or like the purity analysis. Or even for the separator, we can also do the thermal analysis as well. So if you are more interested in all these service, you can we have a brochure, battery materials and analysis brochure. You can scan and download it here. And talking about our battery failure analysis capability, and we focus on lithium-ion battery, but also we are able to do an analysis on all kinds of battery as well. We have 2D and 3D real-time X-ray, and we can identify any failure mode. And as you can see here, this is 2D X-ray. We can using this technique to identify any visible contamination within the battery. At the left side is a control battery. It's a good one. And the right side, you can see some impurity show up here. And also, we can further investigate the degradation of the lithium-ion battery at a grain level or even atomic levels using our broad-beam iron polished, it's called PFIB, plasma FIB, and SEM or TEM, a variety of the microscope technologies. And since lithium-ion battery and battery component and materials and ranging from all the different sizes, just as Dan just mentioned that, we can do different depths. We can also do different scales, starting from the atomic scales at angstrom or nanometer, and then go to the particle scale at microns or nanometers, and go above to the electrode scales, close to the sub-millimeter or millimeter, and eventually even go to the full EV pack. So we have a variety of the techniques can be used to analyze all different materials or components at different scale. Other than that, we also have some other capabilities within our EAG laboratories. So we can focus on different composition. We can do chemical analysis, and we can do thermal stability analysis, impurity survey using our variety of the techniques like ICP, XRF, GDMS, etc. And we can also do the phase identification, or we can also run the battery cycling test and within our battery lab. So this page is just a very comprehensive summary of all the capability or application we can do within our EAG laboratories. And no matter it's cathode, or it's anode, or it's electrolyte, or it's the full battery, or just a separator, we can do all types of test or measurement. And then this page can be downloaded, and if you scan this barcode here. And as we received a lot of questions during the registration, so I'm going to answer some of them, and then my colleague Dangzheng and Kelly will answer some of them as well. So here, many people ask that they heard of the new battery lab, then where it is, and what's the capability of our new battery lab, and is it possible to arrange a tour? So yeah, absolutely yes. Yeah, we can arrange a tour if you are local interested. And our battery lab is located in Sunnyvale, in the South Bay area. So here is our main Sunnyvale lab, the materials calculation lab, and failure analysis lab. So our new battery lab is just about 0.1 miles away from our main Sunnyvale lab, and just next door to Home Depot, so it's easy to find. And when you walk into our battery lab, And the heart of a battery, the new battery lab is the dry room. So we have a dedicated dry room, and in the dry room we will also have a argon-filled glove box. And all this is used to disassemble and assemble the batteries. And many people ask, what's the size of our dry room? So our dry room is around close to 500 square foot. And people also are curious about how many people can work in the dry room simultaneously. So the dry room is designed can take up to 4 people at the same time working together. And you can also see here we have a chemistry hood in the dry room, so we can also do some chemistry in the dry room. And talking about the dry room dew point, that's also one question many people are interested. So this dry room is very standard dry room, can go to minus 40 degree F. And the next most important room in our new battery lab is the cyclers room. So many people asking what kind of batteries can we do the cycling test, and how many battery can we test at the same time? As you can see here, we have several types of cyclers. The biggest one is our pack cyclers. It can cycle up to 4 full EV packs at the same time. And we have another cycler. This one is designed for cylindrical cells as well as coin cells. It has 108 channels, so which means we can cycle up to 108 batteries at the same time. And we have another two. One is for prismatic cells, which has 8 channels, and also we have a coin cell cyclers just dedicated for coin cells, which has 4 channels. And also we have 2 environmental chambers, which has the full humidity control from 0 to 100%, and also the temperature range is from minus 40 degrees C to 150 degrees C. So we can do accelerated battery cycling test in our lab. Also, we can do by control the current or control the potential, and when during the cycling test, both mode. And other than that, one more important technique we have is the potential stat. We have a gamma ray interface 5000E potential stat, which enable us to do the electrochemical impedance measurement. And people asking what kind of potential range and current range can this potential stat measure? So this can measure up to 6 volt and then up to 5 amp. And this is just a standard EIS spectrum. And after this, we also have a microscope room within our new battery lab. So far we have 3 microscopes. First one is the Keyence digital microscope equipped with a laser-based elemental analyzer. Also, we have a SEM with EDS function. It's benchtop SEM. It's very small, but it's very convenient. And also this SEM equipped with an air-free transfer system, which means we can directly transfer the sample from the glove box and to this SEM without exposing to any air, oxygen, or moisture. And the third one is our blue 3D blue LED scanner, which you can see here. And we can scan the outside structure of the battery or some small devices. And it cannot penetrate inside because it's not a X-ray, but it can get a very accurate structure of the outside. And many people ask us, can we do quantitative analysis with our microscopes? And our Keyence microscope and the SEM microscope, they are both benchtop, so they can do kind of like a semi-quantitative. So the main use is to see if the element is present or not, and if it's usually need to be about 1% to show the presence. So if you want to do the real quantitative analysis, we have a high resolution SEM with EDS, and in our nano lab, at Milwaukee. So we also have that capability, and it's very convenient nearby. And next one equipment we have in-house is a particle size analyzer. So this particle size analyzer is equipped with a multi-laser technology, and you can measure a broad range of particle size. And of course, people ask what kind of size or particle size can we measure. So it can measure in dry mode, which is just put a powder inside, or it also can measure in the dispersion mode, the wet mode. So by dry mode, it can measure down to about 100 nanometers, and from 100 nanometer to 2.5 millimeter. And for the liquid dispersion mode, it can measure down to 40 nanometer, from 40 nanometer to also 2.5 millimeter. And in our this chemistry lab, other than the particle sizer, we also have a small chemistry hood. We can do active materials extraction here, and if our client asking for the extract the active materials from the electrode. And right now we are also getting an auto titrator into our chemistry lab. So in the near future, probably near future, I mean in a month, we'll be able to titrate the HF concentration in the electrode, or also measure the conductivity of some species in the electrolyte. And that's everything we have in-house. And other than that, we also have, as I mentioned, that we have air-free transfer systems, which is good for a variety of the techniques, not just for our benchtop SEM. We also have that for our TEM and for our DuraBeam and PFIB, and also a lot of XPS and some other capabilities. So, and also we have a cryoplasma FIB, which is very close to our lab, and then it's designed for to use for the large cross sectioning and also the compositional analysis. Also because it also has the EDS capability. And right now we are building our prototype coin cells, which will enable us to test the electrode performance. Which if some client asking for testing or evaluating the raw material and anode material, so we are able to do that as well. So we have the prototype procedure to make coin cells. And also we are getting the gas analysis tools in-house very soon. Right now we do this in our New York lab, but we are going to get the same instrument in-house soon. So we are able to analyze the swollen cells, pouch cells, and see what type of gas generated inside. And so that's basically what's our capability within our lab and around the EAG laboratories. So next one, I would like to transfer this to Dongjun, another battery scientist, and he will give you more answers for the questions you submitted. Right, Dongjun.
Thank you, Daniel. Hello, everyone. So I'm Dongjun, and I'm working as a battery scientist in Eurofins EAG almost a year now. And I would like to continue the presentation with some of the frequent requests that we are getting. And the first one of these is, what are the key failure modes in a battery that we can observe? And like this is, next one, please. This is actually, there are multiple things that might be happening, but before going into details of this, I would like to talk about the figure that you see in this slide. So normally in a battery, what we want to see is the capacity versus time, or capacity versus cycle number. It can be differentiated into 3 different regimes, and the portion that we are focusing is mainly the mid regime, in which it is the operational mode. And we want to see this as long as possible, but in some cases, this can be pretty short, as many of you might also noticed. And the reasons that can cause to this might be coming from the materials itself, such as like manufacturing defects or any internal impurities might cause this to shorten significantly, or anything during the operation, any stress factors such as electrical abuse, thermal abuse, or mechanical abuse can also cause this lifetime to be really short because of the defects that they introduce. And all these 4 are related with the cell level, but in a system where we have multiple cells, then imbalanced cells can also cause shorter lifetimes in the system. So in here, we would like to focus on which failure mode is happening in that particular example, and try to solve and try to understand the mechanism behind it together with our clients. Next one, please. And this figure, actually, I really like this figure. So it summarizes all the three stress factors that can be implemented to the battery during operation: mechanical abuse, electrical abuse, and thermal abuse. And although they start with different mechanisms, actually where they end up is most of the time it may be similar. So all in all, each one of them can interact with each other, but the thing that we're most afraid of is to create internal short circuits. And in some cases, these short circuits may degrade the cell in a safe way, but in some cases it may not. And it can cause the thermal runaways, which increases the temperature, and then there will be unfortunate accidents that might be possible. So we would like to understand the failure modes and prevent these happening for our clients. Next one, please. And the next question, the next thing that we would like to talk is, most of the time we get the questions such as, what is the analytical method? What is the best or optimal analytical method or technique that you are using in your failure analysis? And actually, the bad thing about this is we don't have an exact answer. It is impossible to have a single answer. Next slide, please. But the best answer is to combine different tools, different techniques together. So that's why it is really important to have large scale of laboratories and possibilities in your labs to answer all these questions. And I think the best advantage, the most advantageous part of being in the Eurofins EAG is we have a large huge family in which we have lots of different tools that we can implement in our FA analysis. But to talk more on them in battery failure analysis in particular, of course, the first thing is electrochemical testing that can be done in order to understand the electrochemical performance of the cells. And we can do impedance spectroscopy or cyclic voltammetry, or directly cycling the cells to understand the performance. Or we can do structural analysis as the first step, in which 2D X-ray and CT scan can show us whether there's any delamination or cracks inside the battery. And all these two actually are non-destructive analysis tools that we would like to go in the first place, because we can still keep the battery without deforming it while doing these tests. The other things that we can do is, in the component level, we can do thermal analysis, DSC, TGA, or we can do structural analysis to individual components. Such as SEM, XRD, XPS. All these tools can help us to understand different features of different components. And then we can do chemical analysis, compositional analysis, or mechanical tests to understand different features of different components, which may lighten up the road to understand which failure mode happened and why they started to happen in that particular battery. And therefore, in all these component-based inspections, it is really important not to produce any artificial defects to have a fair result. And in order to do this, you need an inert atmosphere, where we use our dry room and argon-filled glow box for this purpose, and all the sample preparation is done under controlled atmosphere. Next one, please. And so in terms of the cycle life performance, what can be done as post-process techniques? Let's say we have a cell that is used, but we would like to understand why the performance was as it displayed. So there are actually many things that can be done, but I classified them into 3 different groups. And the first one is electrochemical techniques that we can apply. And there are multiple options: electrochemical impedance spectroscopy, galvanostatic cycling, or cyclic voltammetry. They all show you different electrochemical steps that are happening in the system that can affect the cycling life of the battery. And in particular, EIS, the impedance spectroscopy, is fast and effective to understand different steps inside an electrochemical system. And as we use the batteries, as they come closer to their end life, as you can see in the classical impedance Nyquist plot in here in this figure, as the cycling number increases, the internal resistance in the cell system increases. So we can monitor this with the impedance spectroscopy and understand where we are in the cycle life of the particular battery. Next one, please. And the other technique that we can implement is to do a structural analysis, like to different components. Because this will also help us understand why, if there's any problem, if there is any shorter lifetime than expected, this might happen due to the kind of degradation of the individual components, either cathode, anode, or the separator. And structural analysis, such as XRD, will help us to understand whether there is any secondary phase formation or any amorphization happening in cathode or anode. Or we can also do analysis, electron microscope analysis on the separator to see any lithium dendrites forming or any kind of defects happening in the separator that is malfunctioning and then causing the battery to have shorter lifetime. And the last class is, next one, please. So the last class is doing a chemical analysis. In some cases, lithium plating may happen, or any kind of decomposition of the product, of the components can happen. And chemical analysis, compositional analysis can help us to detect these. For example, XRF is commonly used to detect any lithium in a specific region, but other thing that we frequently see with our projects recently is we get some swollen batteries, as you can see in the image here. So some batteries can cause reactions, can undergo to the reactions in which gaseous species might be produced. And in this case, RGA analysis, in which we take a sample from the gas and try to understand what kind of composition it has. This also helps us to understand what might happen during the operation and what caused the battery to fail. So next one, please. And the other thing is, so some of our clients are coming from the battery field, but some of them are not. So in some cases, they just have the battery in their system and they want it to last as long as possible. But sometimes it is really important to understand the expectations from a battery in terms of its lifetime. Therefore, we get requests for accelerated life testing time to time. Next one, please. And how we can do this is, as you might know, batteries are designed to last for several years, and we cannot wait several years to understand what would be the lifetime of that battery. So we need to shorten the lifetime to several weeks, and in order to do this, we have actually 3 options in our battery lab. We can increase the rate of cycling to reduce the time for reaching the cycle numbers. Or we can introduce temperature. We can increase the temperature to accelerate the reactions that are happening in the battery, and we can go to the results quicker in this way. As you can see in the first graph, as you increase the temperature, the expected lifetime of the battery, the expected number of cycles that it can undergo is getting shorter. Or we can push the nominal limits. We can overcharge or over discharge, or change the depth of discharge as it is implemented in this graph. Then it will also allow us to shorten the lifetime of the battery deliberately. And then with these results, we can estimate the performance of the battery in the nominal use. And next one, please. And with this, actually, we have more to share, but at this point, I would like to leave the stage to my colleague Kelly to talk further on the rest of the presentation.
Thank you. So as mentioned, I'm Kelly, and I'm the battery analyst on the team. So I'd love to dive right into how material analysis of cathode, anode, and separator degradation correlate to state of health. So state of health is a battery's overall current condition relative to its original state. And we can measure this through capacity fade, internal resistance, and ability to deliver power. And we can see this in our cathode, where phase transition and structural degradation occur. And we can begin to measure this through XRD and Raman. We'd begin to see loss of active material that we can further look into with SEM, or electrolyte degradation with FTIR and Raman. We can also see it in our anode. This would be more of cracking and material loss with SEM, lithium plating with SEM as well, or XPS, and our solid electrolyte interface growth with XPS or Raman. And with our separator, we would also see thermal shrinkage and melting that we can also look into with our SEM or X-ray, chemical degradation with our XPS and FTIR, or dendrite penetration with SEM and X-ray. So now we can begin to see what tools we have to show such material and cell degradation, but with cycling. So once we obtain the cycling data, we can actually analyze it in many ways, but here are some common routes such as the discharge capacity. So you can see in this plot, we can do a discharge capacity for cycle number, and we seen in the purple, and we would tend to see our capacity fade. We can also look into our Coulombic efficiency versus cycle number, and that would be our percentage ratio of charge delivered to our charge stored during charging, and that we can see with the orange. And now we would only start to see a decline if our electrodes are reducing its ability to store and release energy. We can also use our voltage profiles, so we can see our potential versus capacity plot. And this is also just another way to visualize capacity fade, either through our charging and our discharging cycles. And another way to look into our cycling data is through differential capacity. So this is when we would apply a low C rate, and so we can visualize our peaks in the charge and discharge. And when a cell begins to degrade, we would begin to see changes in peak location, height, width, and area. So such as, when we see a height decrease at constant voltage, we would begin to see a loss of active material, or a height decrease with voltage shift, we would tend to see loss of lithium inventory, such as electrolyte degradation or lithium plating. And now the battery lab deals with various types of battery chemistries. So we can compare our analytical need between a liquid electrolyte type and solid state type battery designs. So we have some overlap. We can look more into elemental composition with ICP or XRF, but with liquid electrolytes, we're going to look more into GC and LCMS for electrolyte and salt extractions. We can look into impurity analysis with Raman, FTIR, NMR titration, and we can also look into our anion-cation quantification or atmospheric species. But with solid state electrolytes, we would begin to look more into the structure. So that would be with our XRD, SEM or TEM, our interface stability with XPS or TOF SIMS, or impurity analysis with GDMS. And now when we're dealing with all these different types of characterizational techniques, we have clients ask how we ensure this air and moisture-free analysis and how to ensure that measurement process does not change the material. So as mentioned, we have a dry box and an argon-filled glove box, dry room and an argon-filled glove box, but we can ensure that air and moisture-free environment by doing our sample preps in the glove box. And then we have various characterization techniques that allow for airless transfer vessels, and this would include cryo-PFib, benchtop SEM, our XPS, XRD, TOF SIMS, Auger, and DSC and TGA. But how we can ensure our measurement process doesn't change the material, we can further dive into non-destructive characterization techniques we have available, and that would include FTIR, Raman, XPS, XRD, XRF, SEM, and our typical CT scan and X-ray. And now I can hand it back over to Dan Sullivan, who will be leading our Q&A session.
All right, thank you everybody for all the helpful information you've provided. We do have a couple of questions. One clarification we just want to make, the XRF is not how we look at the lithium concentrations. You can do an estimate for that, but we have other techniques like XPS and EOS and ESD that we can do to determine that kind of materials. I did want to go to the questions that we got earlier submitted, and one of the first questions was, how many batteries can we cycle simultaneously? And I'm hoping that Daniel, you could answer that question.
Sure. Yeah, as I just mentioned that we can cycle different size of batteries. So for the full EV pack, we can cycle up to 4 EV packs at the same time. And if it's cylindrical or coin cells, we can cycle up to 108, since we have 108 channels. And for prismatic cells, we have 8 channels. And by using the different adapter, we can also increase that number to 108 channels, since we have a cycler can hold that many channels. So,
all right, thank you, Daniel. The next question we had is, how large of a sample can we actually work on in the glove box? I know that with different car batteries, things of that nature, this is a question we've had before, is how big a thing can we actually get in and do airless transfer type work on? And John, I'm hoping you can answer that question.
Yep. So we can, we have a fairly large glow box, but it is still like glow box, so we are limited by its size and the transfer unit that it has. But we can, I can say we can comfortably work with samples that are 10 inches or 15 inches in dimension, comfortably in our glow box. Yep.
All right, thank you, John. The next question I had is for Kelly. What type of materials analysis can be done with airless transfer? What are the restrictions, and are we going to expand our capabilities in the future?
Yeah, so to recap, the material analysis that's done with airless transfer would be anything from our cryo-PFIB, SEM, EDS, XPS and XRD, TOF-SIMS, OJ, and our DSC and TGA. And we do have some restrictions that would include our sample size. So we typically want to work with something like less than an inch, but can be as small as 1 to 2 centimeters. We have to ensure that our samples are completely dry. This is put into consideration when we're doing sample washing, so we need that extra time to ensure how dry it is, and to ensure that our samples are conductive. So this would be typical, for an example, for SEM. If we don't have a sample that's conductive, that we would maybe inquire more into a gold sputtering method. And expanding the material analysis, I'm not sure on that part. I don't know if the battery team knows any more expansions on this, but that's the information I have so far.
Thank you, Kelly. I had another question for you, Kelly. Basically, the question was about what types of defects or what leads to the shortening of battery life and charging time, and are there ways that we can talk about to minimize those effects?
Yeah, so there's various reasons for shortening of life and increasing charging time. So this would begin from the capacity loss in our anode and cathode degradation. We would begin to see internal resistance buildup. So that'd be the growth of the SEI layer, electrolyte decomposition, or structural breakdown of the electrodes. And this electrolyte degradation would occur due to high temperature and voltage conditions. We'd also see lithium plating when there's excessive charging rates or low temperatures, and separator degradation when there are high temperatures and overcharging. We'd also begin to see thermal runaway due to overcharged, overheat, or being discharged too quickly. And we can try to minimize this by moderating our charge rates. So this would be avoiding fast charging and high voltage that tend to strain the battery. We can control the temperature in any way that we can. So just trying to keep the battery within a safe temperature range to reduce this degradation. We can optimize charging cycles, so in the way that we would prevent deep discharge and overcharging, and just in general avoid operating the battery at extreme states of charge. We can also implement a advanced battery management system just for that better charge and discharge control. And in general, just starting to use high quality materials to minimize degradation.
All right. I did have a quick question for Daniel. Someone had asked, what's the typical turnaround time for an FA battery? I know typically it's 5 to 7 days for a standard. Can you give say if that range is correct, or if there's a particular breakdown for different types of failures?
5 to 7 business, that's pretty standard turnaround time for a single technique. So if a FA analysis, including multiple techniques, and then, yeah, if it's possible to do it simultaneously or in parallel, then that's still 5 to 7 business days. If there's a sequence in sequence, that like let's say we need to tear down the battery first, then that'll take maybe 5 to 7 business days, and then we need to do subsequent analysis on the component isolated from the teardown, then that's another a few business days. So it all depends on how the FA procedure will be.
All right, thank you, Daniel. The next question I had is for Duanshan. What are the differentiating factors between a fire-affected lithium-ion battery and a failed fire-caused battery? Can you give us some insights on that?
Yeah, so the main difference is the initiation point of the fire, but so in terms of the battery, if let's say the fire started externally and then it affected the battery, so the first things that will happen is, so as we know, batteries don't like high temperatures, but when they feel high temperature, they will start degrading much faster. But if the battery itself is causing the fire, then there's a more serious issue with that battery in particular. And for differentiating them in the post-process, if you're not too late where the fire like killed all the evidences, but we can understand it from the components of the battery, because in case of battery that is causing the fire, the components, individual components will fail, and that battery will not be operable anymore electrochemically. So we can understand it by analyzing the individual components, electrodes, or the separator, whether that battery caused the fire or what happened to that. But in the first case where the battery is affected by external fire, it can still be operable, although it is not with the full capacity, it can still be operable. And we can try to understand it with electrochemical analysis tools, or also doing a post-mortem analysis as well.
Thank you, Duanshan. I'm not sure who this question should go to, but there's a question about if somebody has a new material for their anodes and they want to look at the energy charge density analysis, how much material should they give you? I mean, they specifically ask about a powder, but how much material do you guys need to do work with?
Yeah, I can also answer this. So we have the capability of building our own coin cells from powder, so we can do the analysis with materials that are almost like 10 to 20 grams, but always more is better, because we would like to replicate the experiments and be sure about the data quality and reproducibility. So like we can work with material as low as 10 to 20 grams, but always more is better.
All right, thank you, Duanshan. This is for Daniel. The question is, with every company trying to gain higher energy densities in batteries, how do we ensure that EAG can address the issues customers encounter?
Yeah, sure. So yeah, every battery company, they are trying to increase the energy density by developing new materials for cathode especially. So, but it doesn't matter what kind of new materials or new structure they developing, and they're still materials. So as I mentioned and Dan mentioned before, we have 26 labs within globally in the EAG. So we are able to characterize basically all type of materials. So it doesn't matter it's a new material or old material, as long as it's materials, we are ready to characterize them. So I think And if there's any new techniques we need to acquire for the new materials, then we are definitely going to do that as long as the client's asking for that.
So there's sort of an expansion to that question. It was what are the state-of-the-art characterization techniques used by all the OEMs to quantify the new materials from new vendors? Do you have a sort of a list or a handful of techniques that make sense for that?
Yes, there's a kind of a list of the characterization techniques like GTMS, ICP-MS, IGA, and XRD, XRF, XPS, GCMS, LCMS, etc. So it's widely used for the different vendors to QC the materials.
Okay, does EAG have any new techniques or emerging techniques that are used for doing in situ or operando techniques to look at the graphite anodes degradation?
Yeah, we are actively to acquiring this kind of new capabilities. And so far, we have in situ X-ray diffraction analysis, the XRD, is connected with a battery cycler. So it can do in situ XRD during the battery cycling. So we have that one in. I think it's already in place, and we are able to do that. And in the future, if we have got more of this kind of request, we may obtain the in situ SEM as well, and also the in situ EIS capability. So that's all within our consideration.
All right, Daniel. Duanshan, how easily distinguishable is the cause of a battery failure? Is it easy to figure out what actually happened? Is it the cathode, the anode, or electrolyte, or something else? How do you go and figure out where that is, or what's happened?
Yeah, that's a great question, and that's the question that we most commonly get. So it is time to time, like most of the time, it is hard to directly detect one component that has failed from the beginning. So that's why we try to collect as much information as possible from our clients in terms of the operation or the environmental condition that the battery was facing with. But in most of the cases, we need to do a full FA analysis for each component inside the system.
This question is for you, Kelly. The question was, how do you test batteries to see if they will perform well in the long-term reliability before doing a test that takes a long time? How do you do this in real life?
So the best way would be just conducting the accelerated aging tests. So we can do this with elevated temperature testing, high current stress testing, or just cycling at high C rates.
All right. So the other question, I think this is for you, Duanshan, is we're talking a lot about lithium batteries here, but the questioner says, are there going to be work we can do with non-lithium batteries, like advanced bipolar chemistries, or is this lab just for the lithium batteries?
Actually, our purpose is to answer questions for all different chemistries of batteries, but as it is dominating the market, the request that we are getting also dominated by lithium, but we are ready to work with, and we are also already working with other chemistries as well.
Okay, great. The next question was, since you're the battery scientist, what are the phenomena that cause batteries to degrade in storage conditions when they're not being used?
Yeah, this is actually this is a wide topic, but I can try to summarize it a little bit. So these are, since the batteries are classified as energy storage material, the mechanism that they store the energy is create a potential, which is kind of like a driving force for chemical reaction between each electrode. And as we leave them in storage, they still want to react with each other to come to the equilibrium. So that's why even if we use perfect materials, there are still some small currents can pass through the separator, which can cause self-discharge, which will decrease the capacity, or any type of temperature variations can also start degrading the components inside, which is also not good for the capacity or the performance of the battery afterwards. Or moisture is also another thing, any internal impurities. So all of these factors, they accumulate over time and they decrease the capacity and the performance of the cells. That's why it is really important to store the batteries in a dry atmosphere with controlled temperature. And we have a separate battery storage unit in our battery lab to do this for this purpose. When we need to store the batteries for a long time, we store them there.
Thanks, Ranjan. So this question is for you, Daniel. The question, I think we talked about this a little bit, but the question was, can we work on standard coin cells, and then test the anode materials, the binder, the loading, and intensity, electrolyte, and all that materials? Can we do that in our laboratory currently?
Yes. Yeah. The question, the answer is yes. We are able to make standard coin cells within our battery lab, and actually we already did that, and for some of our clients. So yes, we are able to make coin cells, testing either anode materials or binder or electrolyte. Yeah. In the future, we are also going to expand to testing the cathode materials as well.
Okay. So then, Donjan, I guess this question leads from there is what's the criteria? How do we decide what technique to use to do this? What about the materials makes us decide to use EDS versus XPS?
Yeah, this is also really, this is where it is really important to have good communication with the client and also get as much information as possible related with the cell and the cell components. And so that's what we do in the beginning of each project. We discuss these and then try to detect the appropriate technique for that particular request. But for example, most of the time it is good to use EDS to get the composition of different elements in that component. But EDS cannot detect lithium, obviously. So we need to use other techniques to see the lithium content of that component. Or let's say we are suspecting any structural deformation, degradation of the component. If it is crystalline, it is good to use XRD to see any secondary phases. But if it is, in some cases, solid state electrolytes might be amorphous in nature, then we need other techniques to use because XRD will not really respond directly to that. So it will all depend on the particular project that we are dealing with.
Okay, thank you. Now, sort of tying on to that a little bit, but what affects the materials, the chemistry, stuff like that, affects the mechanical strength of cells? What's the effect of pressure on cells?
So the mechanical property, actually the pressure has two sides. So some pressure is good for cell performance in the beginning because all these components, they need a good contact with each other. So some pressure can help us to get more contacts in which will decrease the vulnerability to lithium dendrites formation. But too much pressure, of course, will break the materials because none of these components, none of the anodes or cathodes are proud with their mechanical strength. They are ceramic materials, oxide materials, which are brittle in nature. So if we start making cracks, then we will decrease the capacity and decrease the performance. So pressure has both ways to go, but it should be optimized.
All right, thank you, Donjan. Daniel, this next question is for you. Are there any new techniques that we're leveraging specifically for the newer technologies, such as the graphene coatings, the iron air, or sodium ion? Are there any particular techniques that we either have or are looking at?
And for this kind of new graphene coating and materials, I think we can generally adapt our existing techniques first, since our knowledge of those can help solve the problem with these multiple material systems. So if a new technique is really needed, then we can go acquire that, or even develop a new method for this kind of new materials calculations.
Yeah. So Kelly, this next question is for you. What measurements generally provide the earliest indicators for the onset of performance decline in the batteries?
Yeah, so we would be looking both at cycling data and impedance data. So we would want to look at any decline in capacity retention or coulombic efficiency, and then just continue to monitor with our EIS measurements.
So this one, go back to Zhuangshan here for a second. What's the best way to find or spot dendrites in the separators? Is that a thing you've seen before? How do you go find those things?
So actually the best method, of course, if it is too severe, then it can also be seen, observed in the CT scan, but most of the time dendrites are detrimental for the battery way before that. So to detect those, we need to use electron microscopy to observe those features, and we need to do like a cross-sectional analysis on the separator to detect the lithium dendrites, and we have a whole other team that is dedicated to do electron microscopy analysis that we are working together. So that will be the best option.
All right, Daniel, you sort of answered this earlier, but you got asked again. Can we set up lab visits? Does EAG allow customers to work in the dry room? What kind of answer do we have for that?
Yes, and lab tour yeah, we provide lab tour is welcome. So just send us the email to arrange that. And for working in the dry room, that's also something we can discuss. We can work it out. Yeah.
So case by case basis, we should have a chat.
Case by case. It depends on how much time you need working in the dry room and how much equipment you need from us. Or you are going to bring your own equipment, and do we have enough space or power for your equipment? Yeah, such as like that.
Okay.
But
so,
yeah, can be worked out.
So I've worked on batteries for about 10 years now, and we always used to have to discharge all of our batteries completely before we could do our work on it. Is that still true? What kind of state of charge can we work with on our new battery lab? And what can we do with non-fully discharged samples?
So as everybody knows that the charged battery, they are very dangerous to work with, especially when we trying to disassemble it. Yeah, as long if by instantly we short it, then it'll catch fire. That's why usually we work with 30% state of charge batteries or below 30%. Then we feel pretty comfortable to tear down or disassemble this type of batteries. It also depends on the size of the batteries. If it's just a coin cell or small cylindrical cell, I think it's okay to work with higher state of charge, like 50, 80, or even fully charged batteries. But if for the big batteries, like the big EV pack modules and a few pounds each, then definitely we need to fully discharge of those before we disassemble them.
Okay,
So
we're
basically case by case, yeah.
We're getting close to time here. We do have one last question that was submitted. There was a question about the accelerated aging, so maybe Kelly, you might be able to answer this, but they were basically asking if you increase the stress, the temperature or the cycling, whatever, say 20%, does that directly go to an increase in the lifetime that you've tested by 20%? I think that's not true. I think there's different theories or different equations used to judge the acceleration, but can you give us sort of a flavor of what kind of acceleration you get?
Yeah, like you mentioned, there's a lot of factors. So I don't personally have an immediate answer. I can definitely look more into it for after the presentation, unless someone else on the battery team has any insight.
Yeah, I think it's not a.
There's
Oh, go ahead.
Yeah, it's not like a linear relationship, but just similar to most of the electrochemical reactions, it has more kind of like an Arrhenius relationship with the effect of the capacity. So it's more exponential. Like when you increase the temperature, let's say 20-30%, then it will have an exponential effect on the capacity most of the time. But in detail, there's much more going on, but that is the general trend that we can
Great.
see.
So it's not a straight linear. We understand that it's higher acceleration than that, and we would work on details with someone.
Yep.
All right, we're very close to the end here. I want to thank all of our speakers for the time and thank all of the people who have attended. And I'm going to wind up, next slide, I think. Yeah, I do want to talk about EAG here. Some of the reasons we believe the EAG is the place you should get your work done is that your client confidentiality is core to our business. We do NDAs. We always behave as though there's an NDA in place. We have a lot of people. I think we have something like 400 PhDs at EAG that wind up, have a lot of experience in the industry and have a lot of knowledge that can help you solve your problems. We can scale to your demand. Since we're part of Eurofins, we have the capability to ramp up very quickly if you need larger types of analysis, if you're going from prototype to full production, for example. We do own more than 2,500 instruments worldwide, so we have a large variety of techniques and tools. We are ISO certified, 9001 and 17025, and we are a global leader for materials testing services, and we've been around since the 70s. So we're here to help you solve your material problems. And now I think I want to hand it over to next slide. So it goes over to Rena. Thank you, Rena, if you can close us out.
Yeah, thanks, Dan. And thank you to all of our experts for this robust discussion and presentation. And want to also say thank you to everyone for attending today's event. If we didn't get to your questions today, we'll be following up with you soon. If you have any other questions, please send in your questions to the email address on the screen. That's customerservice@eurofins.eag.com. Also want to mention that I've added a few links to our resources in the chat window, so please check those out. And also want to mention that we will be exhibiting at the Advanced Automotive Battery Conference, AABC, in Las Vegas next week. Stop by our booth 818 to meet our battery lab manager, Daniel Liu. Once you leave today's webinar, you'll receive a survey on the presentation, and we would appreciate your feedback. On behalf of Eurofins EAG Laboratories and our experts, thank you for joining us today, and have a great rest of your day.